There are some subsets of robotics that are moving from science fiction into reality. The ability to program living tissue and robotics 1/100th the size of a hair is just one example. To give us a look at what is happening with biological interfaces for robots, we're going to talk to Jinxing Li, who has created a robotic skin that can act as a biological interface and nanorobots that can be programmed to treat disease in a living animal. Well, you've already created a biological interface through an electronic skin. How specifically does that work?
Our recent invention, which called NeuroString, is a soft implantable device that can be implanted in the brain to monitor like dopamine, serotonin, which are related with, for example, Parkinson's disease and depression. So what is new here is that we are using a soft tissue mimicking materials to make electronics. So the mechanical property is similar to our skin. That's why we call it electronic skin. Because it's so soft, which is different than our conventional like silicon or metal-based electronics, so that it will not damage their biology when you chronically implant it in the brain. So that's the advantage we are having.
So, what specific technologies have you developed to interact with our bodies?
Wearable device which can monitor diabetes, for example, and other disease, to monitor different biomarkers to really predict the disease at its onset. In this case, we can prevent many severe disease, thus to significantly reduce their healthcare cost. And if many diseases can be prevented and predicted, in that case, I believe our average longevity of human beings can be extended to 1 century for everyone. And what we are doing, we are really trying to detect the biomarkers that is directly related with certain disease. So that we can really to use them as a medical tool for disease diagnosis.
And you've also developed morphing electronics that can adapt to its environment. How have you gone about designing those specific devices for the body, and how do they differ to what's currently on the market? Why are they better?
So it's designed specifically for pediatrics or for children. It has a very interesting mechanic property called viscoplastic, or is similar to silicoted. It's soft enough that we can stretch it, but when you stretch it, it will become longer. So that's kind of similar to our tissue growth. So in that case, if we implant this device on our children's body, under, for example, the vagus nerve or sciatic nerve of our children, they can grow together with the tissue without causing any compression to the nerve. Otherwise, you will need a replacement surgery, which is very painful and complicated. So with our mobile device, we can use this for chronic pediatric neuromodulation.
So, once this device or nanobot has served its purpose, what happens to it? How does the material break down in our bodies?
We are using this soft electronics with mechanical properties similar to tissue. So in that case, it will generate much less inflammation and it can stay in the body for much longer time. And of course, we can also use like biopolymers, biodegradable materials to make these implant devices. And for the microbiologic devices we are working on, we can directly use materials that can directly break down in the body.
And what does the future of healthcare look like from where you're sitting, given all of these advancements in these technologies you've developed?
I think the overarching goal, as I mentioned earlier, is that we should really have the healthcare infrastructure near to our human body. Could be wearably implantable in your home, in your car, so that we can really, you know, do, for example, do the health exam every day. It's like because many diseases they go bad because we didn't realize there's a disease ongoing in your body, and I think that's the most important role is really to prevent and predict disease so that we can really reduce healthcare cost and improve their life longevity.